All right, welcome back everybody. Strength of materials. I want to talk a little bit about chapter 10 and then go into chapter 11 a little bit in Poisson's ratio. So chapter 10 starts with conversation about engineering materials, which we talked a little bit about in class, but I just want to emphasize this a little more. I'm going to make myself a little smaller. Sorry about chopping my head off, but if I point it up, there's a skylight that makes it a little bit bright. So we have the ferrous metals and we have the non-ferrous metals. And remember, the predominant component in the ferrous metals, Fe, is iron. And you will get magnetism, right? A magnet will touch it. So there are a number of different ones. We have cast irons, and we have steels, and then there's the list under each one. You should be familiar with that. Like you should know that concept coming out of here. Material science is a fascinating area of study. So if you get the chance to take classes on material science, you should, because there's a lot of new materials, but there's a lot of old materials that we use all the time. Non-ferrous, lacking iron or the omission of iron, things like aluminum, titanium, brass, bronze, copper, all of those kind of things are on the non-ferrous side. So this is a good little chart to keep in mind. Now, then it goes through and does pros and cons of a lot of different materials. And like I said in class, it'd be really good for you to go through and at least read through these and try to understand a little bit about the pros and cons. There is a numbering system to our materials. So ANSI, American Institute's, AISI, American Institute Standards, is going to put these out. I don't know why that's not ANSI, ANSI, American National Standards Institute, but maybe the AISI is a different organization. But we do refer to them, on some numbering system, like a 1036 would be a plain carbon steel, and these are all steels. So it just has everything to do with the alloy in the material, and alloys are going to give you different material properties. So if you needed a stiffer, more rigid steel, then you could stick an alloy in there and make that property appear. I think in the very beginning, they do have a conversation about properties. They do. So in the very beginning of the chapter, right after they do the stress strain curve, they talk about different properties of materials. And so when someone says this is a high ductile material, what's that mean? You can look up ductility and read about it. Okay. All right. Then we did have the conversation about allowable stresses. So make sure you're kind of familiar with that, allowable stresses and calculated stresses. So obviously calculated stresses are the calculations that we make based on our statics work. So we find out the load in a member, we take that load, divide by the area, we come up with a stress. That's a calculated stress. And we typically want to compare that to an allowable stress to say, hey, this is good, this is not good. All right. So that's mostly chapter 10. Factor of safety was in there. We did that in class. So be familiar with that. Just remember that the failure stress goes on top and the allowable goes on the bottom. So factor of safety should be some kind of a whole number like 1 or 2 or 3, or it could be 3.5, something like that. But the failure stress is always a bigger number than the allowable stress. So that should set up some kind of a factor of safety. Okay. If you're given the factor of safety and you know the allowable, then you can calculate the failure stress. Or if you're given the factor of safety and you know the failure stress, then you can calculate the allowable. So that's typically how we use it. Elastic, inelastic behavior, we will cover later in the term when we go to do design work. All right. So that kind of gets us through 10. You got some problems in there, but I want to move forward and talk a little bit about chapter 11. And chapter 11 is stress considerations. So we're going to do these individually, one at a time, but kind of in the real world, you will stack these up in a problem and think about each one. So we'll start to do that towards the end of the term. Right now, we'll just do them one at a time. The first one, Poisson's ratio, that's a mu, Greek letter mu, okay? And it's the transverse strain over the axial strain. So let's remember what strain is. Is our symbol for strain, right? Epsilon, and it's equal to some kind of change over the original length. Now that's if you know those two pieces of information, and this obviously would be a calculated strain. I know the delta, the change, and I know the original length, we can get the strain. Now, if we're talking about a long rectangular piece, right? What we've kind of learned so far is axial. And we probably should start to put a little bit of a notation so we understand which way we're thinking. So the axial strain is going to be how much it changes along its axis. So this would be how much it changes along its axis. And then, so, you know, that could be very small. Right? This little delta change. The length axial is going to be the overall length. So that's kind of what we've done so far. We've talked about elongation. Elongation is this. That's delta along the long axis, okay? And then this is the original length, and this becomes the strain along that. So Poisson's ratio is the transverse over the axial strain. So as something stretches, that cross section has to, you know, that material's got to come from somewhere. It comes from the cross section. The cross section shrinks. So when the cross section shrinks, see if I have another device here. Oh, I've got a pencil. No, a pen. Perfect. This dimension, right, is going to shrink. If it's a square, then it shrinks proportionally on each side. If it's a rectangle, then it's going to shrink different on each side, and you'll have to calculate those separately. So this change in dimension is the transverse strain. This change in dimension is the axial strain. So Poisson's ratio is a material property. So it's different for steel, it's different for aluminum, it's different for copper and for wood, okay? So we talk a lot about different material properties. We've had E, material property, right? Modulus elasticity. We've had yield stress, that's a material property. Our yield stress is different based on the material. Now we have Poisson's ratio, another material property, okay? And we'll get more. This one's super handy because it allows us to calculate the transverse strain based on mu and the axial strain. So on these problems, you typically calculate the axial strain first. Remember that the axial strain is equal to, here it is, delta over L. And the transverse strain is going to be equal to delta over L. But these are T's and these are A's. All right. So here's how it sets up. Poisson's ratio is going to be equal to, so delta T over L P and delta A over LA. Where if we're given this, let's say this is 30 inches, and we'll say this is 1 inch by 1 inch, and we'll say this is steel. We'll just say it's mild steel, which is the 36,000 yield steel, we should be able to start putting some numbers in here. So I'm going to look up Poisson's ratio for mild steel. That's going to be in the common materials here. And Poisson's ratio, where is it? Way out here. Notice it doesn't change much for different steels. Okay. I think maybe this is a little inaccurate table, but they don't change much. That's true. So anyway, mild steel, A36 looks like it's a 0.25. Notice it's unitless because it is a ratio, right? All right, so 0.25 goes here. We don't know the transverse change. I haven't calculated the elongation, but I can do that as long as I put a load on it. So I'm going to put 40 kips. So hopefully that doesn't put us outside the yield, but we'll have to see. So when you do these kind of problems and you want to calculate any kind of delta, you first have to know that it's within that elastic region, right? Comes up, goes over, comes up, breaks. Here's the graph. It's got to be here in this elastic region. And I have to verify that it is within that elastic region. So how do I do that? How do I calculate stress? P over A. So I'm going to do that here. Tensile stress is going to be equal to 40 K over 1 inch squared, 40 KSI. Well, if this is mild steel, 36 KSI is our limit. So this is over the limit. I cannot calculate any deformation. I stop the problem because it's past the yield, it's permanently deformed. It's a big problem. So you always want to check your stresses first. All right, so we're going to adjust the load to 30, which gives me 30 KSI, which makes it under the limit of 36. Okay, so now I'm good to go. I have 30 KSI of stress. Everything's fine. I do need to calculate the elongation because I know the original length, 30 inches. I don't know the elongation. I know the original transverse, that's 1 inch. This is what I want to know, is how much that cross-sectional area changes in one direction. You can only do one direction at a time. All right, so how do we get this elongation? There was an equation for that. We know that E equals stress over strain, which equals P over A delta over L, right? And that's all axial. This is always axial when we do this. Well, I should be able to do that, right? P is 30K. A is, and I'm dividing by 1 inch squared. That's on top. Delta is, don't know that one. And original length along the axis is 30 inches. And I can look up E. Well, I know it. I'm just done it enough, and you probably know it too. Just don't make a mistake. 30, 1, 2, 3, KSI. And I left it in KSI because I have kips here. Okay, so that should give me delta. Now, the other form of the equation, you know, is delta PL over AE. So you can use that one too. It's the same thing as what I just did. I just kind of derived it here. All right, let me run this real quick. Guess you get to watch and see how a TI works. I just put in numbers, and that's my top number, right? actually, I'll do it this way. So I'll put in the P and then I'll multiply by the L, 30. And then I'll divide by the A, which is 1. And then I'll divide by E, which is 30,000 because I'm leaving everything in kips. So it looks like it's 0.03. And that's inches because the kips cross out and we're left with inches. Okay. Now, why did we do that? Well, because now we can put it in here. Now I know that, I know that, I know that, I know that, I don't know that. So Poisson's ratio allows you to calculate the transverse dimensional change. So I'm going to rewrite this equation solving for this. So I'm going to have mu is here. And then this is just going to move over. So I'm going to go times the 2 axial. And you need your axial notation on this, right? That's important. And then this looks like it multiplies across. And all that's equal to, all right. So that's what it solves out to. And then I just stick numbers in. This is 0.25. I should be able to do this, 0.25. This I just calculated at 0.03 inches. My original length is 30 inches and my length transverse is 1 inch. That's the original transverse length. And all that is equal to what I want to know, which is the delta change in the cross section in one direction. This normally is a really small number. Just beware. All right, so I got the 0.03, 30 divide. Looks like it is 0.0003025 inches. That is the change in this cross section based on this 30,000 pound pull on mild steel. Very important for us to be able to calculate that. Okay. So go through this, rewind it, fast forward, whatever you need to do, and then go after the homework problems and see how it goes. Hope that helps. And thanks for letting me go online today, Thursday. And I will see you next week. Let me know how the homework goes. So I have a clue that this worked or didn't, so I can do more.